Right. This is a solution to one of the examples that I gave you before the semester ends on the very last lecture. So with this particular one, we have a swap subroutine that has two parameters. They're both pointers to 8-bit unsigned integers. And then we have two global variables, x and y. And then we have the main subroutine that is setting up everything. So let's go ahead and tackle this particular problem. What I'll do is I'm going to write the code on the side. I'm opening up a mouse pad right now. There we go. So we'll put the mouse pad on the side, so this way we can see the C code as well as the assembly code at the same time. So there we go. Alright. So we'll start with main because the entry point to the entire program is main. Before we get to main, the first thing we need to do is to initialize the stack pointer. So that's LDID with a 0. And just for the purpose of identifying the beginning of main, I'm just going to put a label here, which is not going to be useful. So in main, we have the first thing we need to do is x equals to 42. And we don't even have an x yet, so we'll go ahead and declare the global variable x. As a global variable, x is just using up a byte in RAM, and since I'm here, might as well declare one for y as well, which is also just a byte. And the initialization, I could have done it over here and just use 42 instead of 0, so I could have done this. But since the actual initialization is done by a C statement inside the program, I will just do that as well. So LDI A with x. So A is now containing the address of variable x, and then we'll do LDI B with the value that we want to put into x, which is 42, and then we'll do a store into what A points to, which is variable x, the value that is in B, which is 42. So that's going to initialize x, and the initialization of y is pretty much the same thing. And B is supposed to be y is supposed to be initialized to 77. So we'll do a store to what register A points to, whatever B has. So this part is the initialization of y to 77. Alright, so that is all done. And we'll put a halt instruction here to mark the end of main. And then the rest of this program needs to set up for the calls to swap. And because the agreement is if a parameter has 2 or fewer parameters, all the parameters are passed by register A and register B. So we'll go ahead and stick with that particular rule. So we just say LDI A with the address of x, LDI B with the address of y. And we can do this a little bit later after we set up for the return address and all the other stuff. So we'll load A with we need to allocate space from the stack first. So we need to load A with a 1, and we want to subtract A from D, so we just say allocate byte on stack, and then what we want to store there is the return address. So we'll do a LDI A with return address. Okay, now if we want this to be absolutely clear, well, I guess that's clear enough. That's okay. We'll store this to where the stack pointer D is pointing to. So now we are storing the return address. So store return address of the call to swap. Okay. So now that we have done all that stuff, we can utilize A and B. And then we do LDIC with the address of the subroutine, which is swap. And then we'll go ahead and perform a JMPC so that we are now continuing with execution at swap. The point of return is right here, right after the JMPC instruction. So return address is defined here. And then we have the same thing over here because we are swapping twice. So let's go ahead and swap one first, okay, just to make sure that that part is working before we stack up another one on top of that. Alright, so that marks the end of main without the second call to swap. Now we go ahead and implement swap itself. Okay, so now we have swap as an entry point, and we already know that register A and register B have special meanings because they are passed in as parameters. And it looks like we need the objective of the swap subroutine is to exchange the values pointed to by register A and register B. And we know that we cannot mess around with register D because that's the stack pointer. But there is a trick here, so I'm kind of debating whether to do this the slightly easier way or the harder way. Well, let's do it. Let's go ahead and do it the harder way, which is sticking with this C code here. And because T is a local variable, it is allocated on the stack as well. And every time we want to allocate something from the stack, we have to decrement the stack pointer. So we have to decrease the stack pointer by 1, just like that. So now the stack pointer D is pointing to the newly allocated byte that has not been utilized yet, and that turns out to be our local variable T. Okay, so let me just comment here, allocate for local variable T by decreasing the stack pointer by 1. The first thing we need to do is to dereference A and put that into local variable T. And we already know that register A is the actual parameter A. And so we can utilize D in this case. So we can say store into register C whatever register A is pointing to. So we basically say, C is the reference of A. And the next one is to store that directly into whatever D is pointing to. In other words, D is already pointing to the storage for local variable T, so we can store that right away into it. So that saves us a little bit of trouble. So up to this point, we have T equals to star A already. The next one is actually a little bit more complex because we don't have a whole lot of registers to play with. So with the next one, with any type of assignment statements, you have to handle the right-hand side first. So we'll go ahead and handle the right-hand side, which is LDC, in this case, the reference B. Okay, so C equals to star B. And we want to store that to whatever A is pointing to. And fortunately, in this case, it's not too bad because we have register A still pointing to, still being a parameter. So we can now say STA whatever C has. So this is actually, it turns out to be actually simpler, much simpler than I thought it would be. And then the last one is to store whatever T has into whatever B is pointing to. But remember, T is what the stack pointer is currently pointing to because we just allocated that. So that makes it pretty easy to deal with that too. So we say LDC the reference D. Okay, so C is star D, and then we store that to whatever B is pointing to. Okay, so throughout all this code, fortunately we have the scratch register C left because register A and B are being used as parameters, and then register D is the stack pointer. So fortunately we have enough registers to kind of hold all the important pointers into registers. So when this is all done, we got a few things to do because we have one extra thing on the stack because of these two instructions. So the next thing we need to do is to deallocate a byte. In other words, at the end of a subroutine, the local variables are not useful anymore. So we have to deallocate it. And to deallocate it, we just have to add 1 to the stack pointer. So now the stack pointer should be pointing back to the return address. So now we can just go for the usual return sequence of instructions, which is first loading whatever the stack point is pointing to into a register so we can jump to that register later on. And because we are not really returning any value in this case, we are free to use register A and B again. So we'll use A to store the return address. Okay, so A is the return address, and the previous one is to deallocate stack space for local variable t, and this one is really just doing star b equals c. Alright, so that we got everything commented. So after we utilize what the stack point is pointing to, which is the return address, then we need to deallocate that as well. So we already have C being a 1 from earlier, so we can just keep doing that. So we can keep whatever is in C, which is a 1, and just add it to the stack pointer. So this one is to deallocate stack space for the return address. And now that the stack is balanced, we can now perform the jump to wherever register A is pointing to. Okay, so we continue at return address, which should get us to the halt instruction here. Alright, so let's go ahead and test whether this program works or not. So we'll go ahead and copy the entire program, put it into my assembler, go to the source tab, and go to cell A1, do Control V, and we want to check column B for any potential errors. And so far so good. Okay, so we don't have any errors here, and these two are extra. They belong to the previous program. We can go ahead and delete those. So we now can look at the RAM file output because there are no errors. It just shows everything is correct, and I'm still suspicious of whether it got all the parameters correct. So in this case, everything works out just fine. I'm looking for cases where we have the use of 2 registers and only one show up in these columns. But since I changed all of these, instead of using the split function in Google Sheets, instead of doing that, I used my own regular expression to deal with it. I'm pretty sure that problem is gone. Alright, cool. So we can go to the RAM file, go to File, and specify download as CSV over here, and just save the file to the temp folder for me, and we'll call this swap.ram. Okay, now that's saved, and now let's switch back to Logic Sim, and we'll do a usual reset first, just to make sure everything is reset to the reset state, and go ahead and load this particular program, which is swap.ram from the temp folder. And this is all done, and instead of single stepping through this, I'm having a little bit more faith in myself now, so we'll go ahead and just run the simulation by enabling the tick and double check the frequency. That's pretty high. Alright, so I'm pretty sure the program is all done, and the reason why I know it's done is because when I look at PC, the program counter is now at 1A, and also when we look at the microcode ROM, it is stuck at location 010, which is corresponding to opcode 01, and that turns out to be the halt instruction. So we kind of know that the simulation is done, so we disable ticks. And what we want to do is to go to the location corresponding to global variable x and global variable y, and make sure that those two have the value that we are expecting. So let's switch back to the C code here, okay? Because x started off with a value of 42 and y started off with a value of 77, we expect those to be reversed now. So x should have a value of 77 and y should have a value of 42. And to figure out the actual address of those particular variables, we go to the assemble sheet and just kind of look up the definition of x and y. Okay, so scroll down a little bit. Okay, there we go. Here we have x defined to be location 41. This is in decimal, and y is at location 42. So 41 in decimal has a hexadecimal representation of 29, because it's 32 plus 9, 2 times 16 is 32, and therefore we have a 2, and then the leftover is 9, so we have a 2, 9. So this is 2, 9, and 2a in the simulator. So now we switch back to the simulator and go to those two locations. So let's go to edit content and go to location 2, 8, 2, 9, and 2a. So there we go. This is location 2a, 2, 9. Let's double check. 0, 1, 2, 3, 4, 5, 6, 7. Whoops. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is location 2a, which also has a value of 2a. Now 2a is representing 42, and 4d is 4 times 16, which is 64 plus 13, because d is 13, and that is 77. So the program does work correctly. Okay. So if you want to, you can go ahead and repeat this code here. Okay, so go ahead and repeat this code, but use a different label. So you have to use a return address 1 in this case, because otherwise it will just go back to this return point. But if you call swap again, it will swap the values back to having x storing 42 and y storing 77. But since it worked the first time, I'm pretty sure it will work on the second time, so I'm not gonna do that part. So I hope this solution to the first practice question is explained. If you have any questions, go ahead and send me an email. It will be helpful if you quote from the video what time, what I said, and ask me about that particular concept, because that really helps me understand. Okay, you're talking about this part of the video, and I can reply to you, quicker that way. All right, so I hope you find this video useful, and I'm going to work on the next one some other time.